So students, in this video, we do a few more R things. In fact, we do one main thing, which is to implement the convolution of discrete random variables in R. So specifically, we're going to cover or create two functions, but the main one will be convo. And what we want this function to do is simply to find the PMF of a sum of two discrete random variables. So this would be implementing the direct convolution method. So specifically, here we're going to restrict ourselves to the case where x1 and x2, two random variables, are discrete and they take values on the non-negative integers, but in a certain range, meaning they can take the value, well, x1 can take the value 0, 1, 2, up to some upper bound n1. And then same thing, x2 can take the value 0, 1, 2, up to some possibly different upper bound n2. So, and in the end, you could then use the convolution for a random variable x that doesn't have an upper bound, but you then need to, I suppose, arbitrarily fix an upper bound such that all the probabilities after that are so small that they don't make a difference in the calculations. What I mean is, consider x1 to be a Poisson with parameter 1, for example. Well, you know it has some probability to be 0, to be 1, to be 2, to be 3, but then the probability of Poisson takes the value 10, for example, is very, very small. Okay, so you could fix arbitrarily n1 to be 10 or something that after that value, the probabilities are negligible. But that's just a comment. Overall, let's focus on the mission at hand, which is to find the PMF of S, which is the sum of those two things. x1 taking those values and x2 taking those values. Now, as I said, we do this in a function, and the arguments of that function are simply two vectors, okay, PMF1. So that would be the vector containing the masses at every value for x1. So the probability, so a vector containing the probability that x1 is 0, then the probability x1 is 1, then the probability x1 is 2, and so on. And same thing, PMF2 is this vector containing the probabilities for all possible values of x2. So that's my arguments, and then the function is going to do the convolution. I'm going to cover this code, of course, but then in the end, we're just going to return the PMF of S. I'm going to explain this, but just to show you, make it a bit more concrete, let's just try. So assuming I haven't made any mistakes, I declare this function. Now I can use it. And what I wanted to do, just to show you, is that let's say that I put PMF1 to be the simplest thing I can have, the PMF of a Bernoulli with probability of success 50%. So I know that then the probability to be 0, which is the first argument, well, the first number in the vector being the first argument, would be 50%, and then the probability to be 1 would be 50% as well. So PMF1 is this. PMF2, again, PMF2 would be the probability that x2 takes all its values, but here 0, 1, with probability 50% for 0 and 50% for 1. Okay, you know that the sum of two Bernoullis should give you a binomial with two trials and 50% probability of success. So you know those probabilities should be, whoops, mistake somewhere. Yeah, I forgot to see here. I got to see here. Okay, this is what I was expecting: a binomial with 2 and 50%. Well, the probability to be 0 would be 25%. Probability to be 1 would be 50%. The probability to be 2 would be 25%. Okay, if we try it again here, and I put I sum, let's say, two binomials that are of size 2 and probability of success 50%. Okay, so basically I'm going to take the convolution of this with another random variable with this as a probability mass function. Then I should get a binomial for 50%. Okay, let's see. Okay, which you can check that this matches the binomial. Well, we can check explicitly the binomial evaluate at every of its possible values, a binomial 4 and probability of success 1/2 should give me the same probabilities here. Okay, so this is just to show you what I want my function to do. But now let's review, well, the code. How do we do this? Now, our first comment is that it's a programming task. Now, I'm not an expert programmer, so maybe some people want to do this in a different manner. Maybe you find a better way that would be fine. I'm just going to present to you my method. And again, if you want to share your own code, maybe on the Ed discussion forum, go for it. Now, and the point is that there's many ways to do it. Here, it's kind of arbitrary, not arbitrary, but it's personal preference. I want to deal with the cases x1 equals 0 and x2 equals 0 separately. So now I'll explain why. But here what I'm doing is I'm saying, okay, the probability x1 is equal to 0, I call this this object, is in the vector I fed my function. It is the first argument of the vector. And PMF2 2.0, it's an object that is the probability x2 equals 0. That would be PMF1. And then I'm redefining PMF1 to be PMF1 but minus the first element of that vector. Okay, because in R, if you take a vector, let's say of the values 1, 2, 3, 4, but then you do what the code is doing. You type okay, brackets -1. This is going to take this vector, but take out the very first element of the vector. Okay, so it's going to spit out, in this case, 2, 3, 4. Okay, so this is what I'm doing. I'm taking PMF1 and I'm removing the probability that x1 is 0, the first element of the vector. Why I'm doing this is because now PMF1 is a vector of size n1, and the first element is the probability to be 1, and the second element is the probability to be 2, and the third element is the probability to be 3, and that's neat. It's going to help me implement the convolution formula. But again, probably there was a way not to do this, but that's the way I prefer to do things. The point is just this: in R, the first element of a vector, it has index 1. If the first element of a vector in R at index 0, then I could have avoided doing this, because then PMF1 0 would be what I want, the probability that x1 is 0. But that's not the case. PMF1, the first element of the vector, as declared here, PMF1 is the probability to be 0, not 1. And I want PMF1, by this I mean PMF bracket 1, I want this to be the probability to be 1. Okay, this explains the little step I'm doing here. Okay, I hope this was not more confusing than was necessary. And then, okay, a few more things before I implement the convolution formula. This is just finding, okay, what's the largest possible value of x1? Well, now that PMF1, remember, is a vector with probability x is 1, probability x is 2, probability x is 3, up to probability x is n1. Well, the length of the vector gives me n1, gives me the largest possible value that x1 can take. Same thing, n2, length of PMF2 is the largest possible value for x2. This is going to be needed to take the sums in the convolution formula. And same thing, n, just n itself, would be the largest possible value for s. Okay, and this of course would be n1 plus n2. Okay, now again, you could do this maybe differently, but I like to deal with the simple cases separately before I implement a loop. Okay, because this, as I said, is a sort of programming challenge. It's not super hard, but it is a bit tricky. We're going to need loops, and in fact, I'm going to do 2 loops, like a loop within a loop. Okay, which gets slightly confusing. You need to think about it. But my point here is, I like to deal with the simple cases separately than in the loop. So I just so let me explain. What's the probability s is exactly equal to 0? Well, it's the probability that x1 equals 0 and x2 equals 0. So it's just the multiplication of those probabilities. Probability x1 is 0 times probability x2 is 0. Okay, so I can deal with this case kind of manually if you want. And also I'm gonna deal with the case s equals 1, also because it's a simple case, manually. Now overall here, I'm going to declare this vector to contain the probability s is 1, probability s is 2, probability s is 3. I'm going to call this PMFS. And again, notice it's not going to include the probability s is 0, because this is found in a separate object I called here PMFS0. Now PMFS, I declare it to be a vector. This creates an empty vector, right? If you do this, then there's nothing in PMFS, but it exists so you can allocate to it value. So then, for example, you can type PMFS, the first element, if I want it to be whatever. Okay, then this is now a vector with 1 element. Okay, but now PMFS1, this is the probability s equals 1. What is this? Well, it should be easy. It's the probability either x1 is 0, and then x2 is 1. Okay, so probability of x1 is 0 times probability x2 is 1, or the probability that x2 is 0 and x1 is 1. Okay, so you add those two quantities. This gives you probability that s equals 1. Okay, and then now I'm ready to implement the convolution formulas, which overall, I'm going to explain the code, but overall what we're doing is we have this for loop. We're going to find the probability that big S equals every integers from 2, 3 to n. Well, yes, I start at 2 because I've already found the probability S is 0 manually, and I've already found the probability S is 1 manually. So I can run my loop from 2 to n. Now, before I go over this code, let me review the formula and also a sort of updated version of my formula, which is gonna help me implement this in R. So just gonna review. What I mean by formula is just the convolution formula. Well, let's first view in the slides here, week 2. Overall, we had this formula, okay? Probability that the sum of two variables, well, here they were called x plus y. In the code, I've called them x1, x2, but it's the same thing. Okay, it would be this in the general case, this infinite sum. Now, of course, I don't need the infinite sum because the domains or the supports of the variables are constrained. So I'm just going to first present like the theoretical formula specific to our situations here, and then implement it in R. So okay, so this is what I've done here. Okay, in our notation, we have S here is the sum of x1 plus x2. X1 takes the value 0, 1 up to n1. X2 takes the value 0, 1 up to n2. Now, I'm going to find the probability S equals every little s here, and little s takes values in 2, 3, 4, blah, 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 up to n1 plus n2. Yes, because I've already found the cases S equals 0 and S equals 1. So this first line here is the global formula. Okay, in the most general sense, the index k would run from minus infinity to infinity. Here we don't have to start at minus infinity. We can start at 0. Well, yes, because x1, the first probability that's non-zero would be x1 equals 0. So I can just in the first step I can simplify the formula to k equals 0, and also I can stop it at little s. Well, yes, I can stop it to little s because here, if you look at the second term here, probability x2 equals s minus k. Well, if k were bigger than s, well, then you would have x2 equals something negative. All those probabilities are 0, so you can stop the summation at s. But there's more. In our code, we've dealt with actually. Okay, we've dealt with the case s equals 1, 0, and 1. But there's another thing I'm gonna do here. I'm gonna separate the case that uses probability x1 is 0. So I'm gonna put this in front. So the first term here, when k equals 0, you see it. The first term would be probability x1 is 0. But this, again, in my code, I have dealt with this separately. So the probability x is 0 is not in my vector PMF1. This is why I'm putting it outside, because it's going to facilitate the R implementation. So you see, but here I'm just, in terms of mathematics, I'm just saying, okay, the first element k equals 0, let's put it in front. Probability x1 is 0, then times, when k is 0, the second term is probability x2 equals s. So let's put it here. And same thing, the very last term would be probability x1 is s. So I put this here, and then here s minus s is 0, so probability x2 is 0. Again, the only reason I'm doing this is in my code, px1 0 and px2 0, they have a special status. Okay, deal with them separately. Now I'm left with the summation. Of course, it now starts at 1 and it stops at s minus 1. But there's one more step. There's one more step. So depending on the value of s, this summation might not need to start at 1 or stop at s minus 1, depending on what the values of s are. Now, let's explain here, because from this line to this line, everything is the same except those red things. I'm starting the summation at something different, and I'm stopping the summation at something that's different. So let's explain that. Here I'm starting k at the maximum between 1 and s minus n2. Why is that? Well, note that if s minus n2 is negative, then the maximum will be 1. So then you would be starting the summation at 1, okay, like in the previous line. So the case that needs explaining is if s minus n2 is bigger, okay, bigger than 1. Because then we would start we wouldn't start at 1, then we would start at whatever s minus 2 is. But why do we do that? It's because when we do the programming, we cannot use a px2 evaluated at something bigger than n2 because it doesn't exist in our code. Okay, so here, you know, those formulas are equivalent and they're both valid in general, but this one, if we implement it in the code, we're going to get into trouble because some of the, you know, PMF2 and PMF1 as well, they're not defined if we're outside of the support of the random variable. So let's take a second to make sure we understand. So again, the case that's relevant is if s minus n2 is bigger than 1. So we are worried that k here is would be too small, making s minus k too big in the sense that it's bigger than n2. And if s minus k is bigger than n2, then of course p of px2 of something bigger than n2, it's not defined in our code. So this is why we're starting this at the maximum between 1 and s minus n2. So to take the specific case of k equals s minus n2, okay, and assume this is positive. So s minus n2 positive. S minus n2, replace k by s minus n2. What do you get? You get s minus n2. So you get n2. Okay, and the s cancel out and you get n2. So that's fine. px2 evaluated at n2, that's fine. It's defined in the code. But you see, if you had evaluated this at something smaller, careful, at the k smaller than s minus n2, then you would have subtracted something smaller, you would have gotten something bigger than n2, and this is not defined in the code. This is why you start at the maximum between 1 and s minus n2. You don't start at s minus n2 because, of course, sometimes s minus n2, but depending on which specific s you're looking at, this might be negative. So you take the maximum between 1 and s minus n2. Okay, I hope this made some sense. And then the upper bound of the sum, similar thing, but now you're worried about px1 k. You're worried that this k here might be too big. Okay, you're worried that this k might be too big, meaning bigger than n1. N1 being the maximum value x1 can take. Because again, same problem, px1 evaluated at something bigger than n1, it doesn't exist in our code. So this is why you're stopping the summation at the minimum between s minus 1. S minus 1 was the thing we had here. The minimum between this and n1. Well, yes, because you don't want to go above n1 because px1 of something bigger than n1 doesn't exist in the code. And of course, we don't need to sum it because it's 0. It's 0. Okay, so this is why this line here is equivalent to this line, because here anyway you're summing things that are 0. Now, just as a note, those are valid bounds in the sense that it's always the case that this minimum is gonna be bigger or equal to this maximum. Okay, you can just double check quickly. I guess it's not. I mean, to be rigorous, you might find. You might think that, okay, maybe this could actually be smaller than this, and then we're summing, the summation doesn't make sense, but we're fine. Here, if this maximum is 1, okay, where we start the summation at 1, and 1 is smaller than this minimum. Well, yes, because s is at least 2, and then 1 is at least 1. Okay, so that's fine. So if the summation starts at 1, this is okay. And then if not, okay, if s minus n2 is bigger than 1, well, what happens? Well, s minus n2, well, is smaller than s1, than s minus 1. Well, yes, because n2 is at least 1. And same thing, s minus n2 is smaller than n1. Yes, because s minus n2 is smaller than n1. Well, put the n2 on this side. This is just saying s is smaller than n1 plus n2, but it's trivially the case because the n1 plus n2 is the very biggest value S can take. Okay, so overall, if you have S minus n2 smaller than this, S minus n2 smaller than this, and 1, well then overall you have that S minus n2 is smaller than the minimum between S minus 1 and n1. Okay, so this is just a bit of stuff to make sure those bounds make sense, in the sense that, okay, this minimum is always bigger or equal to this maximum. Okay, that is the formula we now, if we understand it, we can implement in R. That was the hardest part, because implementing this in R is then fairly easy. So let's go back to the code. Yeah, so we were up at this step. We find PMS1. Now again, the loop is going to run for all the values from 2 to n. Now PMFS, okay, so this, okay, the probability that S takes the specific value S. Okay, now here, I guess there's another little complication to explain. If n2 is at least or it's bigger than S, bigger or equal, then this is the first term in the. I'm dealing with the first term in the summation I had over there. Okay, let me just go back for a second in my PDF. Okay, I'm just implementing this part, px0 times pxs and px1s times px20. This is what I'm doing this first step. Okay, so but of course the point is I need this if else, because if S was strictly bigger than n2, well then PMF2S here, this wouldn't exist, okay, because it would be 0, but it wouldn't exist in my vector PMF2. Okay, so this is why if S is smaller than n2, then yes, I can have this term PMF1 0 times PMF2 S. Okay, otherwise just return 0. And same thing, if S is smaller or equal to n1, then the first term in the summation, well, the second term in the summation I had over there, that is dealt manually in my PDF formula, would be, okay, probability x2 is 0 times probability x1 is S. Okay, otherwise 0. And then I can implement the formula, the summation formula that starts at well, that starts at this. It was the maximum between 1 and S minus 2. Okay, I think in the formula I had written it in the other direction. Maximum between 1 and S minus n2. And then it ends at S minus 1. Well, minimum between S minus 1 and n1. And then I just need a for loop to compute this sum. Okay, this is the sum running for values of k from this thing to this thing. So for k in some start to some end, and then this is just the formula. PMSS, PMFS, S is PMFSS that I initialized here. Okay, and then plus whatever the formula is saying, PMF1k times PMF2 S minus k. And of course, this is a for loop, so it's going to go for all the values of k between those two bounds. Okay, close this for loop, close the second the first for loop, okay, because this is running for all the values. And that's it. Okay, that's it. I've done it. Then I return everything. Remember, we dealt with the case PMFS equals 0 separately. So then in the end, I return a vector. The first value is the probability to be 0. And then this is a vector that contains all the probabilities to be 1, 2, up to n1 plus n2. Okay, a little tricky to do. And now again, well, I've already declared it before, but let's do it again. I just do a few checks, okay, that it did what I wanted to do. Well, this is a check I've done before. So this gives me what I wanted. Let's do a check that's slightly more involved. I'm just testing my code that it gives me what I expected to give me in cases where I know explicitly what the PMF of the convolution is. The whole point, maybe I should have said, is that usually the convolution of two random things, like a binomial with the geometric, you won't know what it is. But in certain cases, we know that the sum of binomials with the same probability of success gives you again a binomial. So here, if I'm summing a binomial 3 1/3 and I'm summing a binomial 4 1/3, I should get a binomial 7 1/3. So this is the probabilities I got with my code. And then if I check them with the theoretical probability for a binomial 7 1/3, you can see that those numbers they match. Those numbers they match. Yes, it seems it worked. It seems it worked. Let's do just one more trial where you could find a convolution of one geometric plus one geometric with the same p should give you a negative binomial with parameter 2 and p. But now, what I said at the beginning is that theoretically the geometric, okay, has support 0 to infinity. But what you can do is just check, okay, let's just check the mass functions for a geometric for the value 0, 1, 2, 3. You see you have those numbers. So then, of course, I haven't gone far enough to have probabilities that now approach 0. If I go to 5, okay, you still get probabilities that are, substantially different than 0. But now my point is, if you go to say 20, yeah, this is what I have in the code. Now you start getting probabilities that are truly very small. Maybe you're not satisfied with this and you want to go further. You want to go to 30 or something. Okay, now you're starting to get something that's really, really small. Okay, but let's say that just I arbitrarily stop the support at 20, then I'm summing the PMF of a geometric with the PMF of another geometric with probability p equals 1/2. Then you see that's my negative binomial. Now, theoretically, this should give me the negative binomial with parameter 2 and 1/2. Okay, R already has the density of a negative binomial implemented. So then I can compare my one with the R1. Okay, element by element to see that they all. Oh, you see, there's a little bit of mistake. There's a little bit of mistake, but the mistake really here is truly small, right? To the power of 10 to the minus 17. Okay, so those numbers they're small. The mistake is a bit bigger for large values because I'm stopping at some value here. Okay, so we're committing a little bit of a mistake here, but it's not that big. Actually, here the mistake is a bit bigger because yes, there's a limit to what we're doing. But let's try. If I had put here 40 and then 40, now I'm going to just match this. Okay, well, again, we're making some mistake, but it seems that it's very small everywhere. Okay, and in fact, I don't really want to get into that, but some of this mistakes is not due to the fact that we don't stop the summation at infinity. Some of this mistake is just some internal R rounding that's going on that I don't truly understand. But let's not get into that. For us, it seems that we have a satisfactorily close solution. Okay, one more thing. That was the hard part, but now we can easily find the convolution of an arbitrary number of variables if they have the same distribution. Well, in fact, we could also find it with different distributions, but let's say we focus on the case that we want a convolution of x1 plus x2 plus x3 up to xn, and all those have the same PMF. Well, I can leverage the power of the convolution of two of them, no problem. Okay, let's do that. I declare a new function that's going to be called convo.n. This is finding the convolution of this thing as the sum of x1 up to xn. Now, assuming here that probability that x1 that they all have the same distribution. So what I feed this function is just the PMF of x, well, x1, but x1 and x2 and x3, they all have the same PMF. And then n is how many of those convolution I want. So do I want the sum of x1 plus x2 or the sum of x1 plus x2 plus x3 and so on. So n would be, well, at least 2, and it could be anything. 2, 3, 4, 5. You can go crazy. But if you go too crazy, then the algorithm is going to take a lot of time to compute. How do I do this? Well, it's simply, if I want the PMF of two of them, I start with that. Then if I want the PMF of the convolution of three of them, I take the PMF of 2 plus the PMF of just 1, and so on. Now I have the convolution of 3 of them. I do the convolution of the sum of 3 with the convolution of 1x. I get the convolution of the sum of 4, and so on. Okay, so here in terms of code, new PMF, I just call this PMF, but you see it's going to be updated. Now, for I from 1 to n minus 1, I'm going to do this n minus 1 times. my new PMF is now the convolution of PMF, 1x, but I convolute it with the new PMF. Now you see, the very first time is doing this is just going to do the convolution of PMF with PMF. But now I have a new PMF, which is the convolution of 2 of them. Okay, but now I go back, the for loop continues, it goes to I equals 2, and now it's going to take, it's going to create new PMF, which is going to be the convolution of 1 of them, x1, with new PMF is now the convolution of 2. So this gives me a convolution of 3. And I do that as many times as I like. The last time I do it is when I is n-1. Well, yes, because when I is n-1, new PMF is now the convolution of n-1 variables. I convolute one last time with x. I get the convolution n times. And that's it. Now I can return new PMF. Okay, so that's magical. Should work. Let's just check. The convolution, this is arbitrary check, but the convolution of a binomial 4 1/3, for example, n equals 10 times. So what is this doing is taking the sum of 10 binomials, each as a productive success 4, sorry, as a number of trials 4 and productive success 1/3. Well, you know, theoretically, this should give you a binomial 40 1/3. So let's check. Those are my probabilities for with function convo.n. And this is then the theoretical probabilities from R. You see those numbers? They seem to match. Again, in principle, they should match exactly, but there's some rounding error going on in R that I'm unable to explain to you. If I call this X and I call this Y, and you take the difference between the two, okay, difference element by element. Ideally, I would have liked to see 0 everywhere. There's some, yeah, I don't know how to explain. There's some rounding mistakes going on. Okay, but I'm pretty sure my code is fine. If you find a mistake in my code, you can let me know. But those mistakes, the difference between the two is so small everywhere that I'm pretty sure the code is good. It's just that I don't know how to tell you. The calculation somewhere are there's rounding going on that you don't get 0, but you get the difference between code and R. Well, my code and R is very, very small. Okay, that was actually a bit tiring. So I hope you follow me relatively well. And if you have any questions, let me know. I'll stop the video here. And I hope to see you soon. So bye-bye for now.